Okay, so we invite Professor Andrea Guerrieri from HESO and APFL to present a fast place and out technique. He's a participant with recognition and a reviewer at numerous international FPGA conferences. His research interests include electronic design automation, security, and of course reconfigurable computing. So thank you, Andrea.
Hi, thank you very much for the introduction. I'm audible from the bottom of the room. Perfect. So the project I'm going to present today is an ongoing effort with the AMD Xilinx Research Labs in the US, and is about speeding up the implementation flow from C to final bitstream. So I will start defining a bit the problem we have. We know that today with HLS we can achieve a relatively quite high quality of result RTL circuit out of C++ code. But we know as well, as we have seen also from the previous presentation, that before getting the actual configuration bitstream that we can download into our FPGA, we need to pass through logic synthesis and place and route. And sometimes this can take many minutes and even hours. So there is still a huge time gap. And it makes FPGA devices absolutely unfriendly devices to whoever are FPGA users and software programmers, especially when they want to justify, and they have to justify their time to their managers. So the main goal behind this project is to try to speed up the design flow from C to place and route circuits from minutes to seconds. But we don't want only to achieve that. What we want to do is to change fundamentally the way we interact with the FPGA from now on in the future, to be able to compile and run on silicon in less than a minute. So now I want to step back one second to give you a bit an overview of what is the HLS technology today. So I want to introduce you a little bit about Dynamatic. Is our dynamically scheduled HLS compiler that we have developed at lab, APFL, and creates data flow circuits using a finite state of components able to make scheduling decision at runtime. So instead of the classic static scheduling technique used by, for example, VT's HLS or many other HLS tools, Catapult or Intel HLS, etc., instead of having a centralized FSM that is designed at the compile time to handle the data flow of the data, we move and delegate the schedule information to special components using handshake signals, ready and valid, that they can make scheduling decision at runtime. So we demonstrated in multiple papers and in multiple applications that Dynamatic can deliver significant performance improvement with respect to state-of-the-art HLS tools, such as VT's HLS, in very specific situations. For example, application with irregular memory access pattern or control-dominated code. I invite you to visit our website and try out our HLS compiler. The second tool I would like to introduce today is Rapid Write. I don't know how many of you heard about this tool, but this is an open source platform provided by AMD Xilinx that provide a gateway to Vivado backend. So you can intercept at any stage of your design flow a DCP, a design checkpoint. You can add your secret sauce, you can do your manipulation on your design, and you can write back another DCP that you can inject in the standard flow. You can manipulate components, you can add your logic, and you can create a final DCP. Now, let's come back to the original problem. I want to compile and be able to run on silicon in less of a minute. How I can do that? So the main idea I had now a few years ago is to try to rise the abstraction from RTL to coarse grain block, data flow blocks. So instead of flattening my hierarchy and try to place and route small lookup tables and flip-flops, I want to preserve my hierarchy and simplify the placement and routing problem. So my intermediate representation, if you want, is not anymore RTL, but will be a data flow circuit. And as I just mentioned before, with Dynamatic, what we do, we generate data flow circuit out of C++. And on the other side, with Rapid Write, what I can do is to manipulate designs that are pre-implemented, put it on the same FPGA, and assemble to create a circuit. From the fusion of these two tools, I created Dynarapid. Now, I want to show you a little bit. This is not a paper presentation. I'm not going into the algorithms about the placement and the routing we adopted for this. So I want just to show you a little bit what are the technical challenges behind this project and what we are still facing. So this is a Dynarapid design flow that we started introducing in Monterey, in California, in March 2024, a few months ago. We generate a pre-implemented library offline once per FPGA device, for example, a Virtex UltraScale, VCU13X, etc. And then what we do at runtime, we generate a data flow graph, we load this module, we place it into the same for plan, we stitch it and route together. And you cannot believe this, but the output is a fully placed and routed design for FPGA in 15 seconds. The same order of magnitude of compiling software code. This is going to be a game changer for all FPGA industry. So now I want to show you a little bit what are the challenges behind this project, especially behind building this library of pre-implemented data flow components. So what we do, and thank you very much also for the presentation from before, because there is a lot of introduction of many of the problems that we also faced here. We start from an RTL description of our data flow components. We synthesize using commercial off-the-shelf tools like Vivado. We generate a synthesized component, and we extract the resource utilization. Then we extract a map of the FPGA device, and we try to generate multiple footprints, okay, of the same component. And what are the technical challenges behind? We want to create efficient shape as much as we can. We want to maximize the density, so minimizing the occupancy of the physical resources of this component. We want to maximize the relocatability. We want to pre-implement this component. We want to relocate as many as possible locations all over the FPGA because we want to build up a circuit. We want to preserve the routability, again, from the presentation we had before, both intramodule, right, and intermodule, because this module, they have to be connected one to each other afterwards. And we should not forget that this module should be assembled, so it should be self-contained. Now, to minimize the occupancy, what we do, we try to explore all the possible rectangular footprints of increasing gate that are wide enough to accommodate a fully routed components. So here, for example, you can see an example of footprint for a simple component. You can see it's very small. We are talking about 10 to 15 lookup tables and flops. What are the technical challenges behind? So there is no direct control of routing resources while drawing P blocks. So we do know how many logic resources do we need, but to estimate the amount of routing resources is clearly not an easy task, especially switch boxes and programmable interconnects point, PIP. Another problem is about the relocatability. We want to move these blocks as much as we can into our flow plane. And we explore all possible anchor locations where we can store, where we can place this module. And again, the technical challenges here is the irregularity of today's FPGA architecture. As we mentioned before in the previous talk, we have columns of DSPs, we have columns of LUTs, we have VRAMs, we have I/O buffer in the middle. So you can see, for example, here, how this is an original module. We can relocate on a different anchor location and works with no problem, both logic and routing resources. While we are moving in a different location, we have problem with routing resources. The yellow lines are antennas, disconnected wires, and we don't have the module, the integrity of the module preserved. Here you can see another example where we have a small component that instead is wide and short, and replacing to another location, we have again I/O buffer in the middle, and the integrity of the module is not preserved. So we have to prune all possible locations to be absolutely valid and to preserve the integrity of the module. Now, I want to tell you something about the routability. So we want to have the module that pre-implemented using the standard commercial off-the-shelf tools. So they are internally routed, but we want also to route them to each other to build up a circuit afterward. So the technical challenges that we have here, as I said before, so the intramodule routing is exceeding the module's boundaries. So especially in our case, we are shrinking as much as we can the size of the P block to host and to accommodate exactly the logic and the routing resources that we need. And then we face plenty of problems with the routing going outside, even though defining of the constraints about the self, the routing inside the P block. And the other problem is the intermodule routing congestion. For the same reason, we are shrinking as much as we can, and we have internal routing congestion. Especially for the IOs, we want to do the intermodule connection and connect these modules with the others. And the IO are scattered inside, and they are not reachable for the outside. So for this also, we developed some algorithms and methods. I invite you to read our papers. Or I can also tell you offline, otherwise I will speak for the whole day, to solve this problem and to handle the I/O connections. You can see, for example, we are not speaking about 5 I/Os or 10 I/Os, but data flow module, a 32-bit fork, for example, we can have 238 I/Os. So the methodology should be really systematic. It's not something that we can do it with our hands or just looking at the design. It's something that we should do it properly using algorithms. So here is, for example, what is happening while we are merging 3 of these small blocks. You see how we have routability errors, all the red lines, and this module cannot be connected one to each other. Now, assembly modules. We want to we want to place the same modules on the same floor plan. We want to build a circuit. We are build up. The problem here is to select what is the best shape. For each component, we have multiple shape and multiple location. We want to select what is the best shape and location in order to build up a functional circuit. And we want to be able to place this module as close as possible to minimize the critical path. Again, just to give you an order of magnitude of the problem, we have for a 32-bit adder 8 possible footprints, which means 8 possible shape with different density, right? Because we have an overhead also on density, and we want to maximize density. And the relocatability is about 60K. So you can imagine the gazillion of potential combination that you have in order to build up your circuit. So to solve this problem, also again, I'm not going to do a paper presentation and show you any equation about this, but we start doing very fast placement techniques in order to generate our circuit and to find a legal solution. We implement a classic simulated annealing algorithm which of course has this problem about runtime, is a probabilistic method. I don't know how much familiar you are with simulated annealing. And the problem here is even more complex, because we are placing heterogeneous modules, and we have also overlapping among them. So it's not that easy. And the second algorithm we implemented is a greedy approach. You can see how it's much more compressed, right? So what we try to do is to place components as close as possible with satisfying the not overlap among them. And the second part is, of course, the routing. We need to route these modules. And we want to use not timing-driven techniques. That means that we don't want to reiterate multiple times to have a solution, but we want to have a solution very quick. And of course, should be able to do partial routing. Our modules are already routed internally. What we need to do is this inter-module routing. Again, you can see here a small example of fully placed and routed design that we generated with DynaRapid. But you can see also the complexity of the routing, how it can be really large. Now, I want to present, yes, of course, we don't need to forget that what we care is about runtime in this project. I want to present a few of these results. Again, our preliminary results. I invite you to look at our paper and the official documents we have. These results are already improved by half. Now we have around 7 to 8 seconds to generate an FIR, and of course, depending on the complexity of design, this time can change. So you can see how the greedy for planar is running in milliseconds. So we are very powerful with this technique, although we are not able to meet what we call the timing closure, in the sense that what we do, we generate a design and we try to meet the frequency that we get during our buffering. But we are able to generate a fully placed and routed circuit in order of 10 seconds with a speed up to 30x, 0.9 frequency degradation with respect to Vivado. I conclude this presentation introducing DynaRapid. Is an open source tool targeting runtime first that is able to complement commercial flow that are instead targeting high quality of results. Is not yet open source. It's going to be open source in a few months, I guess. You can see here some of the potential applications of DynaRapid. We want to simplify access to FPGA to software programmers. Can be used for doing fast prototyping, emulation. When you want to use FPGA in the loop, running and compiling in a few seconds. Accelerate hardware-software co-design when you do the design space exploration, etc. Or for custom instruction set extension, for example, MicroBlaze, RISC-V, NIOS, etc., etc., and many more. So thank you for your attention. I'm open for any question. Please stay tuned for the publication of DynaRapid.
Thank you very much, Andrea.
Thanks for your presentation. Currently, it's a really promising tool, I would say, a changer. I'm wondering, okay, it's open source, so probably it can be extended. So in that line, so you're working with Xilinx or AMD, as whatever. So how difficult it would be to basically port DynaRapid to other vendors like Lattice or Altera?
So let's say all the techniques we are using here, if you want, are completely vendor agnostic. What we are leveraging here is the P-blocks utility while creating these P-blocks and all the P-blocks techniques that are available in Vivado. But if the same are available in other vendors' tools, we can use it. The other thing is related to the rapid write. So as you know, the bitstream generation is always something that is confidential and proprietary. So now what we do, we use rapid write, and we use their API so to have access directly to the information of the FPGA. But of course, if there is, with other vendor tools, we can definitely try that.
Thanks.
Hi.
Hi.
I work on similar problems, and usually you have a problem to control the routing quite, yeah. And even if you can constrain bounding boxes or something, Xilinx always keep routing constraints as soft constraints. And then there are issues like sometimes you have to drive a 0 into something. For example, if you use a DSP block or block RAM, and the 0 is generated in the routing phase but not in the placement phase. So bounding box constraints for placement constraints for these lookup tables are not part of the whole thing. Of the design, and they will add it later. And if you cut out your module and this lookup table is outside, you will actually read a 1 instead of a 0 and these kinds of things. So problems get severe if you get high density. Yeah. So if you fill your bounding box to more than 70% or something, then how do you fight that one?
So just to repeat the question, how we solve the intra-module routing to have it self-contained. So what we do is, I have actually some backup slides, but I don't know if they are accessible, no worries. What we do is try to center our block. So I can show you here, for example. So I don't know if it's really visible, the P block drawing the purple box here. And you can see that the routing resources, the switch boxes, are actually outside here. So what we try to do is to center our block to have routing resources internally. So what we do is to try to map and draw in the P block to contain all the routing resources. And this allows us to have everything self-contained inside the module.
That's not reliable. The trick for that one is what we do. We build a fence around and we build kind of a hard macro and preoccupy all wires that should not be used.
Okay.
Yeah, so we generate kind of a blocker, if you want so, by preoccupying wires beforehand, and we generate a macro for doing that one, and then you are safe that it works. Just playing with placement is not reliable. It will work if you fill your bounding box with less than 50%, but otherwise you get be bitten by that.
Yes, thank you for this. There is also another point that I wanted to say. So here is not any design we want to use with this technique, but is a finite set of components, and these components are our small data flow component that we use in Dynamatic, which I think you know also very well, are very small component, up to 50 lookup tables, 100 lookup tables, are not complex design, and this allows us to have full control of our P block.
One last question.
Yeah. Thank you for the presentation. I've got two questions. So from an application point of view, I mean, are you aiming for a certain category of applications, or is it like take any applications like filters or controllers or whatever, and it would work here?
Let's say the goal behind this project is to try to speed up and try to have FPGAs in the loop and use it in a debug cycle very, very fast. So the application, whatever you can map in C, you can write in C, you can run on your FPGA. For sure, this is not the work for doing readout, for example, for high-speed data sensor, right? So the readout will always be an HDL design, super controlled, cycle accurate. What you can do here is to accelerate a kernel, for example, and for doing filtering or CNN or many other functions.
I mean, to be able to do this in only 10, 15 seconds, it seems like the holy grail to me. So I'm just wondering, and maybe I should not ask you the question, but more the FPGA vendors. Why aren't they doing this?
Why? So why they are not doing this?
Why do they not apply the same methods as what you do?
Again, this is a very research. We published in a top conference at FPGA. In Silicon Valley, they are going to see this work, and probably other vendors will go into the same direction soon.
Yeah, sorry. Hi. I was just wondering if you were aware about a reticle project from the Washington University, which is pretty similar as yours, and if you had any difference between their project and yours.
No, I'm not aware of this project, but if you can share any information, I would be more than glad to look at this.
Okay, let's thank Andrea again, and we move on to the next.